Hey, what's up, guys? Today we're gonna do this one. Energy of simple harmonic oscillators. Should be pretty easy. I actually gotta study for some things pretty soon. I got a on-demand essay on in English class right now. So yeah, let's start. Also, I'm gonna play some music because it kind of gets boring. Alright, so student sets up a harmonic oscillator in which a mass is attached to a spring with constant K. It's attached to a wall. If the student changes the initial displacement from x to 3x in terms of energy, what will the new mechanical energy be? It'll be 9 because it's the x squared. That's the energy. Yes! Okay. Also, I upgraded the mic. I don't know if there's a difference, but there should be a difference. I put like this new thing on there. In which of the following times is the magnitude of net force on the oscillation mass equal to 0? I'm pretty sure it's either at the peak or at the rest. Crest and trough, I'm pretty sure that's what it's called. I can't be this one or this one because there's multiple. Also, it can't be 2 and 4 because look at that, it could also be at 0. So it has to be 1 and 3. Yeah. Okay, let's see the reasoning behind this. According to the second law, if the net force is acting on the mass is 0, then the acceleration of the mass will also be 0. So to solve this problem, let's use the graph to find when the mass of the acceleration is 0. A mass undergoing simple harmonic motion will have an acceleration of 0 when it reaches its maximum speed, and therefore its maximum kinetic energy. According to the graph, this mass reaches its maximum kinetic energy at 1 second and 3 seconds. So the maximum of the net force on the oscillating mass will equal 0 at that. So when it's asking, yeah, okay. I think I understand. You guys understand. A cart of mass m is attached to a spring that has a force constant K. This thing should be pretty easy. Pretty easy. Kinetic energy is 3/2 of the total mechanical energy. This should be light. So the what? That is attached to a spring that has a force constant K yeah, and the other end of the spring is attached to a wall. The cart is then pulled a distance a from this position and released from rest. Released from rest, the mass oscillation back and forth with a period of t. How does it have oscillation if it's like this, you know? Should I just pretend like it oscillates, like it goes bop, bop? But like, how would that work? Nah, I guess it'd work if it was like this at rest and then it compressed and then was able to compress. Okay. Okay. Alright, so oh, brother. Maybe this is a stretch. I'm stretching this right now. But if everything is the same, and the only thing that's changing is the distance, and you need to make that. This is a stretch. 8, 6, 3.8. 6. Yeah, that was a stretch. Okay. Half. Really? Really interesting. So you were supposed to. I was thinking about using this, but I don't know how to. I guess you could just do that, yeah. But then, what is this? What is the A? What is A squared? Amplitude. Ooh, okay. Also, we were supposed to make it it never said to make it. Oh, in terms of A, I did not see that. This is insane. Okay, so it's actually giving us numbers this time. Okay, good. 0.5 kilograms is attached to an ideal spring. Okay. All we gotta do is just find the stuff. And that equation is 1/2 kx squared. Right, so this is. Oh yeah, I almost fell for this one time. It's not meters, it's centimeters, which means it's 0.2 meters. I think this is just 0.04, right? Yeah. K is 125. 125 times 0.02. No. 2.5. That's the amount of energy in joules. Let's go. So now all we gotta do is 2.5 is equal to K is equal to 1/2 kx squared. We already know all of these things. Plus 1/2 mv squared. Since the only thing here is changing is the velocity, we can just find that super easily by just plugging in some formulas. Okay, so we just so times 2, and then so we can just get rid of that, and then that, and then minus kx squared. What is kx squared? What is x squared? 1/2, 1/4 minus. What is k? 125. And then this is 0.2 times times 1/4. Okay, yeah. This is making sense to me now. It's making sense to me. Should be this. Should be this. We're just gonna put this just for insurance purpose. Ba-bam. That should be that. Then you just divide it by the mass. 0.5. Yeah, okay. And then you square root this. If I get this wrong, I'll be so sad. It's 3.1. 3.1, please. Yes! Okay, bonus question. Let's get this right. Is the magnitude of the net force on the oscillating mass. Can't beat these things because of processor. At what time is the magnitude of net force on the oscillating mass? Oh wait, it can't be that. I think it is that, right? Because it's the same principle. Oh, there's potential energy. When potential energy, let's think about this, guys. When the potential energy is the highest, means completely stretched. It has the least net force. Because there's no forces acting on it, no momentum. I mean, momentum isn't really a force. I think it's this. Bruh. It's okay. Mass has a minimum potential energy as it passes through the equilibrium point. It's accelerating. It will have an acceleration of 0. What? Actually? Yo, wait, this is good information. It has an acceleration point of 0. It has acceleration of 0 as it passes through the equilibrium point. Oh. So, the further away it gets, the more acceleration it'll have. Because the more force it'll have. Oh. 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 So when it's at equilibrium, when it's at the equilibrium point, it has 0. Ooh, okay. Okay. This is crazy. And when the potential energy is 0, it's at the equilibrium point. Okay. But Alright, I'm gonna complete this off camera. But you guys will see the 100% that will come here. The purple that'll come here next time I do physics. I can walk away.